Okay, so we're continuing our 5.6.1 test review. This is going to be part B. I'm not sure if there's going to be a part C or not. We'll see how far we can get. But this question says, a curved section of a roadway is in the shape of a circular arc, 410 meters in radius. It is horizontal, not banked. The coefficient of friction is this. What is the maximum safe driving speed? So we know that V max, this is one of our formulas, is mu g r. So let's plug in what we have. We have 0.4, we have 9.8, and we have 410. So my answer is 40.089 meters per second, which is E. Okay. All right, so this is a curved section of roadway with 240 meter radius, but it is banked at a 73-degree angle. What's the maximum speed? So from lesson 5.2, page 31 of 42, in the example rounding a banked curve, we learn this formula, and they derive it if you want to see where it comes from, but I would just write it down honestly. So this is tangent of 73 degrees is equal to v squared, which is what we're looking for. We're going to fill in 9.8 times 240. I get v squared is equal to this big number, and then I have to square root it to get this, which is b. Oh, I went too far. Okay, let me change colors. Okay, this one I just drew a picture of and kind of thought about, so let me see if I can talk it out. A ball is tied to length of string. A student holds one end and whirls the ball in a vertical circle. So we have and there's the string. First she whirls the ball very fast, and then she gradually slows it. When is the string most likely to sag? And if I'm thinking about it, I mean, having done this before, I think it's most likely to sag at the top, because here we have both the force centripetal and the force of weight, whereas at the top, if the force of weight is greater than the force centripetal, this is going to sag. Okay, so I put the top of the circle. Okay. This one was a little bit rough because we had to do Pythagorean. I'm sorry, not Pythagorean, quadratic. So let me write out what we have. We've got a mass of this, 3 kilograms. We have a radius of 75 centimeters, which we have to convert to meters. And we have a distance from the floor of 200 centimeters, which is 2 meters. What else do we have? So when I did the free body diagram of this, and I kind of drew the line of the ball going in a circle, I said, okay, the force of weight is going to be equal to the force centripetal. And the first thing I did was I solved for velocity using this, and then I plugged in what I know. My masses cancel, and I get v squared is equal to gr. So v is equal to the square root of gr, which is the square root of 9.8 times, this is my r in meters, and I get this for my velocity. Okay, I'm going to change colors for my next part, because the second part is a kinematic equation. They don't ever go away. Do this. Okay. So what I did was I did it in the y direction. So I have y is equal to y-o plus v-o-t minus 1/2 a-t squared. And this is because of the direction of weight. So we're looking for the span of time when it hits the floor. So when it hits the floor, y is 0. Initially, y is going to be 2.00 the meters. And then my v sub o I just found. I'm looking for t. This is 9.8 t squared. So I'm going to rearrange this so that it's a little bit easier for quadratic. So I have 0 is equal to negative 4.9 t squared plus 2.711 t plus 2. Okay, so if I'm using this for my quadratic, let me pull this up here. I have a is equal to negative 4.9, b is equal to 2.711, and c is equal to 2. And the quadratic formula I'm using, I'm searching for t, so I'll be t is equal to b plus or minus the square root of b squared minus 4ac over 2a. So let me plug in what I have here, and I get 2.711 plus or minus the square root of 2.711 squared minus 4 times a is negative. Sorry, I'm running out of space again. And all of this is over 2 times a is negative. Now keep in mind, time can't be negative. So that's going to kind of govern whether or not we add or subtract here. So let's continue here. I get 2.711 plus or minus 4.11 over negative 9.8. So I'm going to go with the minus so that I can have a negative on the top, negative on the bottom, and get a positive time. So I'm not going to do add, I'm going to do subtract, and then divide, and I get this, which is D. Super long problem. Okay. All right. Oh, this one I have literally no work for. I just kind of thought it out. So he's talking about this ride. If you've ever been on these are awesome. Where it says to test the safety of the ride, the owner stands cloth dummies inside the cylinder. This is just encouraging. Each dummy has a unique mass and unique height. At first, the owner operates the ride normally, but after the ride is in the vertical position, he slows the speed. Which dummy will fall down first? And it's whichever one is up here at the top. Because as it slows down, the centripetal force is not going to be able to hold them, and gravity is going to overcome the centripetal force. So that's why it's this one. Okay, let's work this one out. This one also has a quadratic equation, because why not? Okay, this is very similar to the one that we did earlier. So we have a ball of 3 kilograms, however the length is 50 centimeters. So let me write that down. Which is this many meters, and then our height above is 190 centimeters, which is 1.9 meters. Okay. So the first thing I did was the first thing I did at the last problem, which is to find V. So at the top, I know that F force of weight is equal to force centripetal. So I'm going to go ahead and do that again. You've seen this at least, well, once for the other problem, but hopefully more than that. My masses cancel. I get V squared is equal to RG. V is equal to the square root of RG, which is R is 0.5. G is 9.8 always, unless we're on another planet, which is 2.21 meters per second. Okay, so the second thing I have to do, and I'm going to change colors here, is use a kinematic equation to find time. Now, so find time. Now I'm trying to figure out how far right of center of the circle does the ball hit the ground. So I'm going to have to find distance eventually, but I need time to do that. So I'm using the same kinematic equation I used last time, and I have y is equal to y initial plus VOT minus 1/2 AT squared. Okay, so one of the things we need to know from the outset is that this is going to, VO is 0. We're not going to use this for our VO, and it's because we are at the top of the loop. If you go back to our former example, we were at like right here at halfway, so we used our VO. So again, our Y is going to be 0 because it's when it hits the ground. Our YO is going to be our 1.9 plus 0.5, which gives me 2.4 meters. So I have 2.4 plus, oh, that's a minus, 1/2 9.8 t squared. So 0 is equal to 2.4 minus 4.9 t squared. And t equals 0.699 seconds. So then the last part of this is using the velocity is equal to distance over time and solving for distance. So that's a VT. Now I'm going to use my 2.21 in my time, and I get 1.54 meters, but all of my answers are in centimeters, so I have to convert to centimeters, and I get 154 centimeters, which is right here. Okay. All right, this one's fairly quick. We're going to use the Vmax formula, which is the square root of GR. R is equal to 0.90 meters. So we plug in our gravity, we plug in our radius, and we get 2.96 meters per second, which is this one. Okay. Okay. An astronaut's weight W on Earth. The astronaut travels to a planet that has a mass 8 times greater and a radius 2 times greater than the Earth's radius. What is the astronaut's weight on that planet? So what I did was I said, okay, is going to be equal to this, where the mass on the other planet is 8 times the mass on Earth, and the R on the other planet is 2 times the R on Earth. So I plugged these in. I have G M P M over R P squared, which is G 8M over 2R squared. This gives me 8GMM over 4R squared. So I reduced this, and I get 2GMM over R squared. So it looks like 2W, which is C.